Right. So next we should move to, so after we introduce both the max flow and mean cut definition, we sort of move to the actual algorithm. This algorithm, it's really just trying to solve the max flow algorithm, max flow problem. Sorry. And after we solve the max flow problem, we sort of need to prove the correctness, and then that sort of like goes back to the max flow mean cut theorem we mentioned about, right? So the algorithm itself is more or less a greedy algorithm. We will see, like we need to tweak the greedy algorithm a little bit to make it work, but more or less it's actually intuitive in general. Um, so um, so let me just repeat what I said just now. So now we want to design an algorithm to solve the max flow problem. The algorithm is called for the Focusant, and the algorithm is really just essentially there are two messages, right? So the first message is the greedy algorithm. It's most of the time it's really just a greedy, right? But just simply running the greedy doesn't quite work, right? So we sort of need one extra observation. The extra observation is really just introduce the notion of augmented passes. Um, right. So for this lecture, let's really just try to examine the greedy algorithm. That doesn't quite work, but it's really just delivers 70% of the intuition. And the next lecture, we will see how this can be fixed by this extra observation, right? So the greedy algorithm, right? So just imagine that we sort of has an input graph that looks like that, right? So now all the capacities are ready. Just imagine all the pipeline has been built, and now we sort of like just you should imagine that now we build the pipeline, but we haven't started pushing the water, right? So you can imagine that you are just incrementally pushing more and more water in this pipeline, but in the beginning the everything is clean, right? So it's everything is brand new. No water is being circulated at this moment, right? So this is what the first step of the greedy algorithm. Start with the flow being zero, right? So this is the flow solution for each edge, right? So what we are going to do is really just that we find a path that's connecting from S to T, where each edge has the flow that's less than the capacity, right? So basically, we sort of want to find an edge, right? So let's really just not look into this little requirement for now, right? So because everything is clean, right? So that we really just need to find an arbitrary legend, and there's a good chance that we can push water out, right? So let's say for the first step, we really found an edge, an ST path that looks like that, right? In order to find an ST path, you can really just run a BFS or DFS, right? Whatever search algorithm that you have to learn, right? We haven't learned DFS, but for the point here is that for whatever search algorithm you have learned, that like, you can easily find a path, right? So it's just really just an arbitrary path. Any path will work, right? So now let's imagine we choose the highlighted one, right? The bolded one, right? So basically, if I look at the path here, right? The capacity unit limit here is 10. This is 8. This is 10, right? I haven't done anything at all, right? So intuitively, what I'm going to do is I just want to start to push out waters here, right? So push out waters here, push out waters here, and push out waters here, right? So I want to push out as much water as possible, right? So basically I'm push out 1 unit, 2 unit, and you can really just imagine that the volume of water get increased gradually. At some point, right, it's going to hit the capacity limit of one of the pipelines, right? The first time we hit the capacity limit is 8, right? So when we gradually increase the throughput, right? Throughput. The first time we hit the limit is 8, right? After we hit late, then we cannot increase the throughput anymore, right? So in terms of algorithm, of course, you don't do these silly things to gradually increase, right? You just check the number 10, number 8, and number 10 again, right? You just take the mean, right? So you take the mean, and then you realize it's 8, and then you sort of push through 8 unit of flows over here, right? So this is how we do that, right? We push through 8 unit of flow here, right? So now the next time we're going to find another path, right? So now this continuous condition start to be important, right? The FE has to be less than CE, right? So the next time whenever, so now this path, we are not going to choose this path anymore, right? So although this is a path that's connecting from S to T, right? But then but then it's not true. So we want to pass such that each edge, we there the amount of flow we are pushing through is a bit smaller than the capacity limit, right? So that basically means that whenever we find a pass, right? So let's say there are 4 pipelines, right? So basically, what we want to find a path that so that whenever we are pushing, we look at the existing flow, right? The existing flow could look like that, right? So there is some sort of margin we can continue to use, right? So it's not working anymore, right? So there are some sort of margin, right? We can continue to use, right? So that basically the intuition is that now these are the margin, the unutilized the capacity, right? So long as every single segment has a little unutilized capacity, then basically we can push through more waters across this pipeline, right? I'm not able to change the color, so for now. So now I'm just want to push additional new flow on top of this existing solution, right? So that's the reason that in this it's very important to check that for every edge in the past we found, it's we are not hitting the capacity limit, right? So in case we find that we find a pass so that actually one of them already hits the capacity limit, right? The rest of two maybe not hitting the capacity limit, then basically we are not able to push more flow, right? So basically, so this also comes back to the like what do we mean by greedy, right? So basically what we are doing is that we find out an arbitrary path and we push out as much water as possible, and we repeat the same thing until we cannot update anymore, right? So now for this case, right, actually it becomes for this case actually it becomes obvious that now we cannot use this bolded path to push through more floats, and then we are going to look for a second pass, right? So how can we look for a second pass? The it's actually pretty easy, right? So because this one is sort of saturated, we cannot delete and we cannot really push more flows, right? So what we need to do is just can chop off and remove the entire edge over here, and then we're just going to run another BFS to find another pass that's moving from S to T, right? In order to do that, right? So let's really just say that let me run a BFS, right? You don't really need a BFS, right? You can just run any algorithm as I mentioned just now, right? So now one natural way, right? And a natural new path we managed to find probably looks like that, right? So let's check whether this path is legitimate, right? So now before, right? So you can sort of imagine like what we are doing here, right? So imagine that you are a water factory, right? So you are really pushing up a lot of waters and then to your client, right? So now you are already operating. You are really pushing out 8 unit of flows through this edge, through the through this the bolded edge, bolded path, right? So now you sort of want to increase your capacity. You want to push more water towards the client so that you can make more money, right? So your candidate path is really just this red path here, right? So what's happening for this red path is right now at this moment it's pushing through 8 unit water, but its capacity unit is 10, right? So that basically means that we have room to really increase 2 more unit, right, using this route. And similarly, the capacity unit of this path or this edge is 2. We are not using any of them, right? So we still have a room of pushing up this increasing the flow of 2 units for this edge, right? For this edge is even better, right? The capacity unit is 9. We are very far away, right? The room here is 9. And for this path, this edge, right, the edge over here, it's actually we are faced similar to the situation of the edge, the first edge, right? So we already used the 8 unit. There are 2 units we can use, right? So if you look at all this number, it's 2, 2, 9, 2, right? So you basically calculate the mean of all these numbers, right? You calculate the mean of all these numbers, it's 2, right? So basically you decide to add the 2 more unit of flow like along this path, right? So this is what's happening here, right? Sorry that I was doing a bit of notes here, right? So basically we are, so originally it was 8, now it becomes 10, it becomes 2, it becomes 2, it becomes 10, right? So this is how we do the update, right? After the update, right? So these are really all the numbers that are that are positive are really used, right? So basically we started to use quite a number of edges, right? The edges that are not used would be this one, and this one, right? These are the not used one, right? So now let's also look at all the edges and examine their situation, right? If you look at this edge, the edge over here, I'm already using 10 unit, right? So the capacity unit is 10, right? So we are not able to push any more flow along this edge, right? So we can delete that, right? Similarly, we can delete this edge, delete this edge. This was actually deleted in the last round, and delete this edge, right? So after we delete all the edges, we really just repeat until we get stuck, right? So what's going to happen next is that if I run another BFS, right, so I actually still am able to find another path that's good, looks like that, right? So it started to become a bit more complicated, right? So the capacity unit limit is 10, I'm using 0, right? So the margin is 10 here, the margin is 7 is 9 minus 2, limit is 9, I use 2, so it's 7, the margin here is 6, the margin here is 10, right? So I can actually push out another 6 unit of flow here, right? So plus 6, right? This is actually what it was doing there, right? So it adds 6 to every single edge along this path, right? So after that, like, let's see what we can do now, right? After we add this one, right? So after we add this one, let's also start to delete the edges, right? So this one is full, 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 right? The rest of them are actually not full, right? So this one is not full, this is not full, this is not full, this is not full, right? So if I run a BFS again on the orange edges, right? So if I run the BFS again on the orange edges, ORANGE edges, right? It sort of leads to a conclusion that S and T are not connected anymore, right? That basically means that for whatever path we found on this graph, it's going to contain at least one edge that's fully utilized. We are not able to find any of the passes such that the flow is smaller than capacity, right? So basically at this stage, like, our greedy algorithm is done, right? So we cannot execute this greedy algorithm any further. What we are doing is that we are crossing our finger and hope that after this greedy algorithm terminates, this it really gives us an optimal solution, because the greedy algorithm really cannot do anything anymore, right? The most ideal case is that whatever that's on our head is already optimal, right? But the bad news is that this is not true, right? At the end, if we run the greedy algorithm, we get a flow of 16 units. But the actual optimal solution is actually 19. There actually exists a way to push 3 more units of flow out of this network, right? So basically that really just implies that our greedy algorithm sort of contains some bugs, right? So this bugs needs to be fixed, and then it's not fixable within a few minutes. So we're going to wrap up this lecture today.